Thank you. Good morning, all. I hope that you can see my screen.
Yes, I can see it clearly.
Excellent. Great. Well, thank you so much to the organizing committee for having me here today. I'm very happy to present on some of the work we've done on colloidal transport, and we'll talk about calcite precipitation, as well as a little bit of looking at metal transport and some other issues as well, too. So first of all, I'd like to acknowledge my collaborators here. So Dr. Jongmook Won of the University of Ulsan did most of the work, most of the heavy lifting that you'll see presented today. Dr. Hyunwook Chu from Hanyang University and Mr. Shaivan Shivaprakash from Georgia Tech have all made major contributions to the work that I'll talk through today. And so what we see here is we know that colloidal particles exist in the environment. We've known about their importance and the effects that they've had for many years. We know these are particles that range from the smallest size on the order of about 1 nanometer to larger particle sizes on the order of about 10 microns. Although usually we bound these at somewhere between 1 to 2 microns and smaller. These are particles which are suspended due to electrical forces, so they can stay suspended in a fluid medium for very long periods of time. They can be mobile, but they can also be retained in porous media. So that means that they can be strained, they can be sorbed, or they can detach. So these are organic and inorganic particles. And as geotechnical and geoenvironmental engineers, we generally are concerned about clays and bacteria. So from a transport perspective, we'll see that these particles can move heavy metals or they can retain them in place. We know bacteria can act as colloidal particles. And we can also see that these particles can act as locations for calcite nucleation and precipitation. So the important thing here is that we know that these particles can retard or facilitate contaminant transport. And so to get some insight into that, we need to understand their behavior, essentially the geochemical effects, and how that ultimately will impact clogging and reduction in hydraulic conductivity. There's been a lot of work done in colloidal transport, but much of that has been done using latex colloids. And in our examples, those are not necessarily representative of the types of colloids that we deal with. We know that clays, especially clays like kaolinite, are strongly influenced by their geochemistry. So that's going to cause aggregation behavior. We know these clays are sensitive to surface charge as well. So whether or not they're mobilized or retained is typically a function of the geochemistry of the pore fluid. So when we think about this, if we look at kaolinite, which is a clay that is very well known for its sensitivity to surface charge, right? And we know that we've got these pH-dependent surface charges. What we're going to see here is we have done quite a few studies on kaolinite from deposits that we obtained in the state of Georgia. So Georgia has some really nice deposits. This is not a perfectly well crystallized kaolin, but what you can see here are a few of the typical book edges that you see as representative of kaolinite. And you also see relatively large particle sizes, right? So when we're looking at the particle here, for example, this particle size is on the order of about 5 microns, but you see a range of sizes as well, too. So we get pieces of kaolinite that have broken or are smaller, and those are able to transport and to interact within the subsurface. So we sometimes see these edge-to-face agglomerations, or we sometimes see edge-to-edge. So it's kind of a messy combination of how these particles are going to interact, but it becomes very important for transport in the subsurface. When we think about infrastructure, these colloidal particles cause a lot of headache for us oftentimes, right? We know that we can see them clogging leachate collection systems and acting as precipitation surfaces within those systems. We also know that they can cause us significant trouble when we're trying to infiltrate or dewater or do oil well recovery, for example. And then finally, they will play a role in MICP, which is a relatively recent, more sustainable ground improvement technique as well. So if we take a look at what this means for us, the particle associations and what that holds in terms of implications for transport, there are a few things that we need to think about. So first of all, we know that our colloid aggregation will be a function of the geochemistry of the pore fluid, right? So if we choose kaolinite, which will be the representative clay and colloid that I'll talk about tonight, or in the morning for you all, what you'll see here is that we know that these can be deflocculated and dispersed, and they transport as discrete particles, but we also know they can aggregate and have face-to-face associations where they form these larger aggregated flocks. So what you see on the right-hand side here is an experiment that we did to measure the flock size of kaolinite. And we did these at constant pH of about 5.6, and we varied the ionic strength. So when you look at relatively low ionic strength or with no dispersants whatsoever, what you'll see is that these kaolinite flocks have D50s on the order of about 18 microns. So that's fairly large compared to the SEM image that we saw earlier. If we increase our ionic strength, though, increase calcium chloride concentration by an order of magnitude, what you see is that those flocks start to shrink, right? So we've made fewer sites, negative sites available for sorption. We've shrunk the double layer, and we see that reflected in the average flock size or the median flock size that we show here. We continue to increase the ionic strength, the salt concentration, and we continue then to decrease the D50 as well. Until ultimately, if we come in and we add dispersants, we'll start to see single particle behavior. And you can see the D50 between a kaolinite that has a dispersant added and the D50 that has a relatively low or vanishingly small ionic strength is almost an order of magnitude difference, right? So that's going to cause a lot of differences in behavior in terms of transport through the subsurface. So let's think about what this implies for us. We know from filter theory that these cluster sizes or the flock sizes are going to be very important for moving particles through the subsurface. If we look here on the left-hand side, what we'll see is a mechanism of straining. And essentially what happens here is we have large flocks. Those are subject to size exclusion. They get concentrated to the surface, and we get the spaghetti strainer effect where those particles are retained and they make essentially a barrier at the surface. But in addition to that, we can also have attachment. So we get methods or mechanisms of interaction for attachment through electrostatic forces. And then finally, we can also change the geochemical conditions and we can liberate particles. So we change pH, we change ionic strength, we increase flow rate, and those particles then are subject to different electrostatic conditions, and they're liberated and they can flow downstream. All of these properties are going to be important for us. In addition, there are kinetic controls between the attachment and the detachment and the straining that become important as we try to model these changes in the subsurface. So, for example, if we're here and we're looking at a solid water-air interface, what we'll see is that we often get attachment of immobile colloids electrostatically attached to solid surfaces, say a silica sand. So that can be a fairly strong and relatively enduring bond as well. Now, if we think about the fact that at the same time, we also have mobile colloids, which are suspended in our aqueous phase, and we have contaminants which are dissolved in the aqueous phase, we know we're going to have interactions between all of these different pieces of the schematic that you see here. And those are going to be important in terms of what we see for changes in our hydraulic conductivity. We'll also see that we can get interactions at the air-water interface. But for our purposes tonight, I'm going to ignore those interactions and assume that we're in a saturated condition. So if we think about this a little bit further, what we will see is that there are kinetics of attachment, detachment, and straining between the mobile colloid and the immobile colloid. We will also see that we've got kinetics of sorption and desorption between our contaminant and the immobile colloid. And then finally, we know that we can have these same sorption interactions between the mobile colloids and the contaminants. So the key that we need to see here is what are those first order rate coefficients and how can we use them to understand how this is going to change both the physical properties of our soil as well as the chemical properties. So let's think about what this means. What are the influences of these geochemical controls on colloid transport? We'll talk a little bit about pH and ionic strength, as well as concentration and flow rate. So we know that the convection diffusion equation can be used to describe this. We can do a numerical solution to this, and I'm calling it semi-empirical as well, because what you'll see here is that we have these first order rate constants for attachment, for detachment, and straining as well. Essentially, what this is showing us is that we know that the colloid concentration in the aqueous phase will change as a function of time, and that will be subject to the flux, so the total colloid flux in the system, and then the rate constants for attachment and detachment, as well as straining. So if we keep that in mind and we take that forward, the thing that we need to understand now is what are those rate constants? And I called the previous solution semi-empirical because we measure those rate constants experimentally in the laboratory. And we do this by column testing. So we've got a flow cell, and this flow cell that you see here is instrumented so that we can measure pressure changes in the first about 7.5 centimeters, the second 7.5 centimeters, and then the bottom 15 centimeters. So we know that this, we can measure pressure as a function of depth. We can change the experimental parameters. We can change the D50 of our sand, the angularity of our sand, concentration, flow rate, and geochemical parameters. So part of what we're trying to sort out here is what is the phenomena that is going on with the colloidal attachment? How does that impact hydraulic conductivity? So is this a blocking function where we have the sand sorption sites and they get filled and the colloids can no longer attach? Or is it a ripening function where we have the sand, we cover the available sorption sites, and then we get sorption of colloids to immobile colloids? So what you'll see here are, well, I'll show you some retention profiles for clays in the column tests that we've performed. And from these retention profiles and some additional monitoring, we're able to draw out those rate constants that we need for attachment, detachment, and straining. The take-home message, though, what I want you to see coming in from these columns, the retention profiles of these columns here, is that we can manipulate the geochemistry, the ionic strength and pH, in order to either facilitate the flow of colloids or down the flow of colloids. So what you see here in this case is on the left-hand side, an instance where we increase the ionic strength, and what that results in is a decrease in straining, but an increase in filtration. So that means that we get depth penetration of the colloidal particles, and they attach electrostatically to the sand matrix or the sand skeleton with depth. On the right-hand side, you're seeing results of column tests where we increase the concentration of kaolinite. So we've got 5 grams per liter in the data that you see here on the right-hand side. And then we've also come in and we've increased the ionic strength as well. And you can see in this case, the blue squares that we have are almost a perfect uniform retention profile here. So we're getting the same number of colloidal particles deposited as a function of depth from the top of our column all the way through to the bottom of our column. So what you see here is that we can manipulate the ionic strength to basically push the colloids as far as we want. So what's important, though, the thing to take home here that we want to remember is that it's the size of the clay cluster or the clay flock that's important, right? So the aggregated sizes are what are governing the deposition profile, not the individual clay particle sizes. You'll see this becomes important as well in the hydraulic conductivity. So we reduce the hydraulic conductivity over here on the left-hand side, and you can see with the purple diamonds that we have, this is hydraulic conductivity that we measured in that first 7.5 centimeters of column height. So we've got flow coming down the column. And as you look within that first 7.5 centimeters, we start to see straining. We see the column clog up. We're at a very low ionic strength in this experiment. We've got very big flocks. So we're basically clogging up that entire first layer, reducing the hydraulic conductivity substantially. When you get down to the bottom, none of the colloids made it that far. So you can see that the hydraulic conductivity there stays relatively constant compared to the initial unflown column. When we look on the right-hand side, though, you'll see, again, we've increased our ionic strength. This was an experiment with calcium chloride again. And you can see here that we have a relatively uniform hydraulic conductivity with depth. So what we've done, again, is we've uniformly deposited those particles throughout the length of the column, which has allowed us to control, or at least to have some control on the hydraulic conductivity of the column itself. So when we look at this, what we're going to see is that we run into a couple of scenarios where this becomes significantly important and can really have substantial impacts on our column behavior. And those primary places where we worry is when we have high pH and high ionic strength situations. And this is really important for us more recently because this is often the case we have when we're doing MICP. When we put those conditions into a column, we can release the fines, and those fines become highly mobile. And people have seen it routinely in the laboratory and in the field as well. So these high pH, high ionic strength conditions can liberate the fines from the soils that we're treating. The other thing that we'll see here is that we can control the heavy metal transport as well. So the breakthrough curves of heavy metals will be strongly dependent on the pH and the concentration of our colloidal particles. We can increase the pH and we slow down the movement of those particles, so we retard the breakthrough, or we can increase the ionic strength and we can facilitate the breakthrough, right? So these changes, especially if you're in cold regions and they're using salt on the roads, these can have substantial impact on your contaminant transport. So let's look at bacterial retention curves and what that implies for us for calcite nucleation. So when we do MICP, we can do this in a biostimulation environment, or we can do it in a bioaugmentation environment. And when we bioaugment, we're essentially pumping bacteria into the soil, pushing them through and then stimulating them to let them do their work. So when we think about this, what we're going to see is that we get bacterial retention in the subsurface. And what you're looking at now is an SEM image of a silica particle. Silica is here, so this is sand. And then what you see up here on the top of the image is actually a calcite layer which is precipitated on the silica particle. We have gone in and added the yellow color to the bacteria, so they're not normally yellow, but we've added it here in this image just to show the effect of how they're distributed. You can see these are relatively well spread out on the surface. You can see in some cases that the enzyme precipitation has been so fast that the bacteria actually cement themselves into the calcium carbonate layers. We can see this also when we do calcite nucleation on a carbonate sand. So this is again very nicely deposited, precipitated calcite that you see here in the background with a relatively uniform distribution of bacteria. But when we look at other types, other places where we see the bacteria come in and do precipitation, you can see that we have aggregation of the bacterial phases. And these aggregates are going to be dependent in part, not completely, but in part, on the pH and the ionic strength that's present in the pore fluid. So think about this. If we have bacteria and we're trying to flow them through the subsurface, we can see that we can have arrangements here where we have face-to-face arrangements. We have some cross, some slight edge arrangements here as well too, but for the most part, these are bacteria that are present in small groups. We can come in then and we can look at changes in our pore fluid conditions, and we can start to see much more alignment in the bacterial phases. So we start to see these bacteria line up very similar to what we would see with our clay particles as well too. We start to see these face-to-face agglomerations, right? And so trying to transport these bacteria through the subsurface would be much different than if we're trying to transport a flocculated group of bacteria through the subsurface here. You can see that we've got edge to edge.
Dr. Burns,
yes.
You have about 5 minutes.
Okay, perfect. Thank you. You can see
that.
Yeah, no worries. You can see that we've got some face-to-face connections here. You can see that we've got edge to edge or end to face as well too. So if we're trying to flow these types of different collections or aggregations of particles, and I'm counting bacteria here as particles, you can see we can do this just by manipulation of the geochemistry. So it's a really powerful tool. It's one that we don't always take advantage of very well, though. So what you'll see then again is that we can also look at retention profiles for bacteria and how that relates to calcite deposition profiles. So what we've got here shown on the right-hand side is basically a column where we had silica sand, And we ran a series of experiments where we had only the silica. We didn't have any colloidal particles present. Then we started adding increasing concentrations of colloidal particles as well. And what we did is we looked at what that meant. If we added kaolinite, for example, what happened to the bacterial phase, which was also being injected into the column as well. So when we added these colloidal kaolinite particles, it turns out that we had a much larger fraction of retained bacteria during injection, right? So those kaolinite particles were able to facilitate the retention of bacteria. They serve as nucleation sites, and that also in turn then comes in and enhances our calcite precipitation. So we actually get increased calcite precipitation in a silica sand column when we have these colloidal kaolinite particles present. Right? So you'll also see in some cases here that we came up to pretty high concentrations of kaolinite. The green and the blue that you see over here on the right-hand side were performed at levels of 1,000 milligrams per liter and 5,000 milligrams of kaolinite per liter. You can see that we get that straining profile here across the top of the column as well, too, right? So we're trying to avoid that because we don't want to create clogging. But you can see that there's some level of colloidal particles which are present, which can come in and help actually facilitate precipitation and, in fact, facilitate a fairly uniform profile of precipitation. So with that, the take-home message that I want you to leave with is the fact that we've always known, right, that the size ratio of these particles is important. But what we have seen in the work that we've done is that the solution chemistry is far more important than we had appreciation for. We know that flow rate, saturation, and the polydispersed characteristics of our clay are going to be quite influential in how these colloids will form, how they flock. And what that means is it's going to impact its retention and its transport, and ultimately will result in a reduction of hydraulic conductivity. It can either facilitate or retard contaminant transport, and it can do the same for bacterial retention as well, too, which in turn then will impact the mineral precipitation. And so with that, I thank you very much. My email address is here. I'd be happy to correspond by email. And if I have any time, I'd be happy to answer questions as well. Thank you so much.
Thank you, Dr. Burns. This is a very detailed investigation of colloidal transport, especially on the mechanisms. A very impressive work. But due to the time limit, we will not have a Q&A. Thank you again, Dr. Burns.
Thank you.